So let's talk a bit more about how threads are actually implemented. And one way of implementing kernels is basically to implement them as kernel threads that are only available for the kernel. And that basically means that the kernel can control everything about the threading, but still might give the user some control of some of the data, for example. To the kernel, basically, a kernel thread is nothing more than a single-threaded user process. I mean, it's just a process where nothing runs inside. And the way that multi-processes are implemented in many operating systems, including Linux and Mac OS, is that you have them implemented using kernel threads. So you have the kernel threads that run inside the kernel, and you expose some of the functionality using system calls. So as a process, as basically user level process, you can call a system call to fork a new thread, for example, to start a new thread. But then what would happen is that the system internally will implement everything, or will basically spawn the new thread for you, and the kernel will control that thread. But it will give you back some of whatever is needed. I mean, if that thread is only supposed to run, for example, in user space, because, well, user space function just called it, then it will run as user space thread. I mean by as user space thread, by giving it privileges equivalent to user space thread. You can also have user level threads, user space level threads, and these would be thread operations without system calls, basically. But at least Linux and Mac OS do not work that way. So let's look at this figure, where you have code, for example, and you have multiple kernel threads in the kernel, running in the kernel. But you have user level processes trying to spawn new thread, and process 1 has thread 1 and process 2 has another thread. And basically, to the way that the process deals with kernel level threads is that it invokes a system call, and the system call basically the kernel handles this and starts a new thread for this process, with basically having only one single thread per one of these processes, but making sure that, well, these threads do not violate what they are allowed to do. Multi-threaded processes are a bit more complex because the previous one just had one single thread spawned. Now, if you have a multi-threaded process, basically, then again, you basically use system calls to start a couple of these or many threads as a user. And then the process control block and the thread control block for each of your threads are stored in the kernel space, as you see here. And basically, you then manage the way that you relate, for example, you manage memory and these things in using the process control block. What memory is this process, is this thread allowed to touch? What memory is it not allowed to touch, and so on and so forth in the kernel itself. And then when you actually do the real scheduling, you'll run this thread for a while, this thread for a while, this thread for a while, but then you'll start running this process, but in that process you just run one thread, right? If you have just one single processor, you run just one thread, and after a while you might actually have an interrupt, or that can be basically because you ran for a long period, and then you basically need to have an interrupt stack per thread so that you save whatever data you have and whatever state you have to be usable again, because then you will basically start scheduling this kernel thread, for example, this thread, for example, yes, this kernel thread, for example, and so on and so forth. So you need to keep an interrupt stack for every single thread. This is how a very naive implementation of kernel threads would look like. It's actually, well, it's pseudocode, so it's not implementation. You cannot say it's implementation. And basically, you can see that you create a new thread control block, and you basically also create a new stack, basically saying that this is the stack size and this is the stack base. And the stack base is basically the memory address that you start the stack with for this thread, and then the stack size is how much memory can this thread use. And then you start initializing some registers, such as your stack pointer, right? So you want stack pointer, which points basically to which part of the stack you're in. You want to set the instruction pointer to, well, basically when you start, what instructions you start with, and you want to set some registers that you need, and then you move that thread into the ready state so that, well, you can run it if there's if it's time for it, if it gets scheduled basically on the operating on the processor.